Good morning, students. So we have already completed our very first module, that is the introduction part. We have already seen what are the various ciphers, starting off with the very basic classical encryption techniques, including your Caesar cipher, and then we moved on towards our a little complicated ciphers, for example, Hill cipher, Wigner cipher, Vernam cipher, Playfair cipher, etc. So towards the end, we also saw what are the basic differences between substitution ciphers and transposition ciphers. We started off with rail fence cipher and followed it with the transposition and double transposition ciphers. That is columnar substitution ciphers. So we have already seen all those basic encryption schemes. And in case if you have any issues with any of those ciphers, kindly let me know. I guess you had some issues with the decryption part of Hill cipher. So if you would like me to repeat it quickly, kindly let me know, or else I can start with module number two. So I need your input on this. Do let me know if you want me to repeat the decryption part of Hill cipher quickly, or else I can start off with our next module, module number two. Okay, so kindly give me your answers. Next module. Okay. What about B division? Okay. Okay. Few of you want me to repeat. Okay. I will quickly yeah, I will quickly repeat it once and let's see. Without taking much time, I will repeat it once quickly. Let me see. Okay, I already have it written, so no issues. So I won't waste much time on this. So we had taken this example. If you see, the matrix is given over here. It is the K matrix. I'm not focusing on the entire problem. I will focus only on the main areas where you might end up making mistakes. So this is the K which you have got, the matrix K, key matrix. The very first step was to find out the determinant. If you remember, it came out to be negative, that is minus 939. So I had already shared a small video on this, how to convert or how to take mod of a negative number. So basically what we need to do is, the very first step is ignore the negative sign, that is neglect the negative sign, and add a value to 939 such that it becomes a multiple of 26. Is it clear? So what happens is, the very first step is I'm neglecting the negative sign. So I need to add some value n to 939 so that it is a complete factor, or we can say complete multiple of 26. So as you can see, if you divide 939 by 26, you will get something as 36.11. So what we want is, we want that to be 37th times, because we want that to be a whole number. That is how we take mod, right? So what we would do is, we will check the 37th times 26, how much the value is. It is 962. So what we will do, we will simply subtract 939 from 962 and we will get the answer as 23. So now many of you were asking me how we came to know that the determinant of that particular value is 23. So this is how we take the value of that negative mod. Am I clear now? Is this part clear how we got that 23? Because it was not solved previously. Now I'm showing you how to solve it. Fine. I've already shared the video also. So now using this 23 value, what we need to do is, we know that we need to calculate the ciphertext. The ciphertext is nothing but, as you know, it is the plain text into K mod 26, where K is nothing but the 3 by 3 matrix we are having. So as the plain text has to be a multiple of this K, so the plain text size you need to first of all calculate. Over here, the plain text is, I guess, 3333, 12 digits in size. So we have to separate it, or we can say that we have to split this plain text into 4 parts of 3 each, and then we keep on multiplying it with the K value and take a mod of each of the individual term, and at the end you will get the ciphertext. So this is how we got the ciphertext. I guess you are not having any issues with the encryption part. The only issue lies with the decryption part. So what we need to do is, in the case of decryption, as I told you, similar to encryption, we need to find out the determinant inverse of K. This is the most crucial thing, and after that we can start off with the decryption part. So determinant K inverse into M mod 26 is congruent to 1. This is the formula I had given, that it simply means if you multiply a value M with the determinant of K that we know is 23, you will get a value which, after taking mod of it by 26, you should get the answer as 1. So there can be multiple answers, but the answer which you get the very first time and which should be less than 26 is your answer. So in this case, we got M to be as 17. So we came to know that determinant K inverse is 17. So any doubts so far? I guess this is also simple. The difficult part lies ahead of this. Kindly let me know if this is clear. Yes, come on. Give me your answers. Clear. Okay. Okay, fine. So let's now move ahead. The next part is the actual calculation of decryption. So decryption begins over here. We need to find out K inverse. Now you only tell me why K inverse. The formula changes over here for decryption. For decryption, it is simply uh, P is equal to C into K inverse mod 26. So for that, we need K inverse value. So K inverse can be found out using this formula. I had already shared it with you. Determinant K inverse into adjugate of K matrix. So now we know that 17 is a determinant K inverse into adjugate matrix. Now I had already told you how to calculate the adjugate matrix. It's simply, if you remember, we need to first of all find out the co-minors, and from the matrix of co-minors, we find out the adjugate matrix. So this was the very first step. Obviously you will get something like this. Now this is not actually correct because we can't have negative numbers and we can't have any value more than 26 because all the operations are done in the scope of 26, mod 26. So what we need to do, just now we saw how to convert any negative value to its mod 26 equivalent. The same thing you have to do for this one, and how many negative numbers are there, you have to repeat the same process for that. And for the positive numbers, you know how to take mod by 26. So in short, I can say that whatever answer you get from that adjugate operation, you have to take mod of that by 26. Simple, and you will get the answer as this. Am I clear now? Kindly let me know. So if any value goes beyond 26, you have to make sure you have to bring it back inside 26. Am I clear? Yes, so this is how we get the adjugate. Now you already have online calculators. You can find out the adjugate easily, but I would recommend that you do it manually only just to revise your mathematics. Clear? So you will get adjugate as this. Now it's basic simple mathematics. Multiply the 17 with 14 and whatever answer you get, take again mod of that and you will get the final answer as this. Clear? So now this is your K inverse. Now we know that we have got one of the values. Substitute this value in your plain text equation, that is multiply this with corresponding C values and you will get the C as in CT values and you will get the corresponding plain text. So now as the key size is 3 by 3, so we will multiply that with the very first three characters, that is whatever you got over here, that is RRL. But RRL has to be converted to numeric values. So that is nothing but 17, 17, 11. And once you take the matrix multiplication of this, take a mod of that again by 26, you will get something as 15, 0, 24, and the corresponding characters for those will be PAY, that is pay. So I hope you got the understanding of how we came out with this conclusion. Fine. So you will get the first three sections or first three characters of your plain text. In the same way, you have to repeat for the next three batches of your ciphertext, and you will get the corresponding plain text. So the beauty of this entire operation lies over here. That is how to calculate K inverse. If once you get the K inverse and the adjugate of K, everything else remains very easy. So am I clear? This is how the Hill cipher is to be calculated and solved. It can come for 10 marks in the question in the exam, so be prepared with it. Fine. So any more doubts regarding Hill cipher? So we have used 10 minutes to revise this. Fine. Can we move ahead? Kindly let me know A division, B division. Fine. Okay. Okay, fine. So let's move ahead with today's topic, that is lecture number 11, module number 2. So we are starting with uh, complicated ciphers, or we can say sophisticated ones. So for the time being, just forget about what we have seen in the first chapter. Those were all classic encryption schemes, which are not used nowadays. We can understand their theory, the fundamentals of those, to study the more advanced ciphers that we are going to start from this chapter. Fine. So we have already seen the basics, the fundamentals, and now we have to apply those concepts over here while discussing the latest ciphers that are actually commercially used today. Fine. So the sub module name is symmetric and asymmetric key cryptography and key management. So what we are going to learn in this module onwards, or in this chapter onwards, or lecture onwards, is symmetric ciphers. So the very first cipher we will learn today onwards is symmetric ciphers. And once we complete all those symmetric cryptography, we'll be starting with asymmetric key cryptography. And afterwards, we'll start with key management. Fine. So this entire module is divided into three parts. First is symmetric cryptography. Second is asymmetric cryptography. And third one is key management. Clear? So let's start with the very first topic of symmetric cryptography, that is the basic terminologies. So I will just quickly revise what we have done, a basic summary. Can any one of you tell me what exactly is a stream cipher? You can use your chat box or you can even unmute yourself. Let me know your answers. What exactly is a stream cipher? I have written something over there, but still try to give me your answers. Stream ciphers. What could be a stream cipher? We have already seen an example of it. I may not have given you a proper definition for it because I was waiting for this module. But I have already covered this in one of your ciphers. Not one, in fact, two ciphers. So kindly let me know what understanding you have regarding stream ciphers. Yes, come on, give me your answers. You can refer the definition I have shown over here, but try to give your answers in your own words. Okay, encrypting a stream of data, which is a type of digital data. Stream of data, fine. Okay, what else? What do you mean by a stream of data, Harsh? How the encryption happens? What is the plain text? What is the cipher text? Come on, B division. Not getting answers from you people. Correct. Okay, like a continuous stream of bits. Okay, fine. Encrypt one bit or character at a time with different key for each bit. Okay, we can say that. Or the key also can remain same, irrespective of the key. Generally, the keys are different. So basically, what exactly the stream cipher is, as you have seen in the case of Wigner cipher or one-time or Vernam cipher or one-time pad, if you remember, what happened is there used to be XOR operation between the plain text and the key. Yes or no? PI XOR KI, and later on whatever operations were performed that can be there. But see what happens. The encryption happens bitwise, correct? So it's basically a long stream of plain text, and there's a long stream of key, and each bit of the plain text and the keys are operated upon individually. That is one bit at a time. Am I clear? Or we can say one unit at a time, where one unit could be either 1 bit, 2 bit, 3 bit, 10 bits, whatever. Yeah, Mihir, any doubts? I can see your raised hand. Kindly let me know if you're having any queries in between. So basically, I'm assuming there is no doubt from your side. So basically, what exactly is a stream cipher? It is nothing but there is a long stream of plain text, there is a long stream of a key, and each unit of that plain text and keys are computed individually. Once that answer is obtained, once that ciphertext is generated, they are later on combined to form a greater ciphertext, or we can say a final ciphertext. Am I clear? Kindly let me know. Yes, B division. I'm getting answers from A today. B division is not giving me answers so far. So kindly buck up, give me your answers. Yes, fine. Okay. So now can you tell me what is the difference between block cipher and stream cipher? We have already seen some examples of block ciphers also. Any idea? This is the very basic definition, or we can say the very basic difference between a stream cipher and a block cipher. Can any one of you tell me what exactly is a stream cipher and block cipher? We have already seen what is a stream. Now kindly tell me your inputs on a block cipher. Yes, come on. Yes, Rishikesh, Isha, Siddhi, Dhruv, Harsh, Rahul. Yeah. Block cipher operates on blocks or groups of data. Correct. In simple terms, we can say that uh, in case of a stream cipher, we operate on each bit or each byte of that data at a time. But in the case of a block cipher, we say that there is a block inside which there are, for example, 64 bits or 100 bits inside. So one block will be processed at a time. So it is not about single bits. Once we complete the entire block, the answer for that block will be written after processing that entire block. It won't be written after each bits or each units. Am I clear? So in this case, we can say that in the case of a block cipher, a unit is nothing but the entire bits present inside that block. Am I clear? Is this concept clear? So you can see this definition. A block cipher is one in which a block of plain text is treated as a whole and used to produce a ciphertext block of equal length. Typically, we have a block size of 64 bits or 128 bits. Whatever is the algorithm, it depends upon that. Fine. Similarly, in the case of a block cipher also, the two users share the same symmetric key. Now, I'm just coming to the concept of the key. As we are discussing symmetric ciphers, as you all know, have only a single key, which is going to be used for encryption as well as decryption. Is it clear? Yes or no? Symmetric key, asymmetric key. Am I clear? Fine. Yeah, we can say like Playfair. In the case of Playfair, the block is nothing but a group of two units or two alphabets. So it is nothing but each block will be treated separately. But in the case of stream ciphers, the block is further reduced in terms of only bits or bytes. So we can say that 64 bits constitute a block in simple terms, right? So now I was saying that can you now differentiate between a symmetric cipher and a symmetric cipher? Yes or no? We have already seen the examples based on symmetric ciphers. Fine. Yeah, Simran. Okay, fine. So the answer is in the case of a symmetric key cipher, the key remains the same throughout encryption and decryption. So the sender will encrypt using the same key and the receiver will decrypt using the same key. But in the case of an asymmetric cipher, one key will be used for encryption and the corresponding key will be used for decryption. Corresponding means there will be a different key, obviously, but that will have some relationship with this particular key, sender's key. Fine. So this is just a representation of how a stream cipher and block cipher differs. Just have a look. On top, there is a stream cipher. And as you can see, a stream cipher basically consists of uh, a series of inputs, that is the plain text PI, and a series of key streams that those are KI. So PI and KI are XORed or any other operation could be there, and whatever result we get, that is the ciphertext CI. Similarly, the decryption end, CI will be XORed with KI and you will get the PI back. This is the basic principle of a stream cipher. But in the case of a block cipher, it is like this. The entire plain text, that is B bits, okay, entire plain text of B bits will be encrypted using the entire key. Now, obviously, the key has to be of the same size as compared to the plain text. Otherwise, there can't be any operation, right? So what will happen is internally, any operation or any function could be there. I'm just focusing as a conceptual diagram over here. Whatever is the key, the entire key will be encrypted. The entire key will basically encrypt the plain text and you will get the ciphertext of the same size. And the exact process in the reverse order will take place while decryption. Am I clear? So this is the basic function of a symmetric key cipher in the case of stream cipher and block cipher. Is it clear now? After this, I will move ahead with the modes of operations. Okay, let me read a question. Will the result be same if the keys are same? It depends upon the algorithm, whatever algorithm you take. For example, in this case, Hirsch, as you can see, the encryption algorithm might have operations such as XORing, it might have operations such as swapping. So you can't be sure that the results will remain same because it ultimately depends upon the operation which is used inside that algorithm. If both of them are using XOR operations, then it will obviously remain same. Am I clear? Fine. So let's move on with the next topic for today. That is the modes of operations of block cipher. It is very important because this question comes for 10 marks. This is the very first topic that we have done so far, block cipher principles. And next up, we will have this topic, block cipher operation modes. So what are basically block cipher operation modes? Basically, now you know what exactly is a block cipher. So what could be the operation modes? We have just now seen in the first module, there is a cipher called as playfair cipher, there is a cipher called as Caesar cipher. So all of these ciphers have their different principles, right? So we need to follow certain modes of operations, and based upon those modes of operations, we can say that a certain cipher follows this particular mode, and this particular cipher doesn't follow a mode, right? So whatever ciphers, whatever block ciphers we are going to learn, they have to strictly follow either of these five modes only. So these are the five modes which are there, which any block cipher, any one of these can be followed by a block cipher. Or if it has its own mode of operation, then it has to specify which mode of operation it has followed, or basically which mode of operation it has been derived from. So as you can see, there are five modes of operations, and if you're creating your own algorithm, then there has to be some sort of significance with either of these five modes of operations. So we are going to learn about them in detail. So don't worry what I'm talking about. I will just explain them one by one in detail. Fine. So just have a look. The very first type or very first mode of operation is electronic code book. Second one is cipher block chaining. Third one is cipher feedback. Fourth is output feedback. And fifth is counter mode. Okay. Any doubts so far? So basically, we are going to learn about the modes in which the various block ciphers work. Can we move ahead? Do let me know. Yes, fine. Okay. Okay, so let's start with the very first mode, which is what we call as electronic code book. And in the exams, you might have you might face a question where you might be asked to explain any two of these, or any two of these for 10 marks, or you can have explain all of these for 10 marks. So it depends upon the type of question being asked. So if it comes for all of these, obviously you have to write in short, depending upon the length of the question, depending upon the marks or weightage of that question. You have to write it accordingly. Fine, I will give you a brief understanding of uh, what are these various modes of operations. So you have to draw the diagrams for each of these modes of operations. So I will first of all start with the diagrammatic representation, and I will explain them one by one. So just have a look. This is the very first type, the simplest of all the five modes, that is electronic code book or ECB. I will first show you the diagram, and then let's try to deduce some important points out of it. As I have already explained, the plain text has to be divided into multiple blocks. So in case your plain text is of size 640 bits, and you know that your block size has to be 64 bits, so it has to be divided into 10 blocks. Am I clear? Yes or no? It's simple. So if you're having a block size of 64 bits, and if you're having a plain text of size 640 bits, so simply you have to divide that into 10 blocks. Now the question may arise, what about unequal partitioning? For example, if it is not a complete multiple of block size, then in case you know what to do, you need to add some random characters in the last block so that it becomes a multiple of the block size. Am I clear? Yes. Kindly let me know. Yes, fine. So very simple principle. If it is not equal to the multiple of the block size, kindly add those many characters to make it a multiple of block size. Simple as that. In the last block, not in any random block. You have to add all those characters in the last block only. Fine. So very simple. Divide the plain text into those many blocks, n number of blocks. You will have the same key which will encrypt the ciphertext blocks, sorry, which will encrypt the plain text blocks, and you will generate the ciphertext for each of the blocks. So ultimately what you will do is you will write the ciphertext block 1, concatenate that with ciphertext block 2, concatenate that with ciphertext block 3 up to block n, and at the end you will get a huge long stream of plain text, sorry, ciphertext that is basically being that is basically a process of encryption after applying the key. Am I clear? This is the very first type, that is electronic code book. Any confusion, any issues with this, kindly let me know. This is the most basic type of operation. Kindly let me know if you got the understanding of this. This is just the encryption part. I will just come back to the decryption part also. Fine? Simple enough? Okay. So let me show you the decryption side. Again, it is same. The decryption process is exactly the reverse of it. The input will be the ciphertext and the key. The key is obviously going to remain the same because we are learning symmetric key encryption this time. Fine. So what will happen is ciphertext block 1 and key will be applied inside this function. This basic function is nothing but a decrypt operation. You can have XOR over here. You can have any function over here. This is just a general diagram of the algorithm. So depending upon the operation being used, it will decrypt it and you will ultimately get the plain text back. The same process, plain text 1, concat, plain text 2, concat, plain text 3 till plain text n. And at the end, you will get back the same plain text. You should get back the same plain text if the operations are symmetrical. Am I clear? Any doubts so far with this? Do let me know. Okay, fine. Okay. So I have written a few points over here. These are just basic points or what I have summarized out of it. The plain text. In this case, the plain text is divided into blocks of 64 bits each. Okay. This is a standard cipher, that is electronic code book. So whatever be the length, the plain text is divided into blocks of 64 bits each. It has one of the drawbacks if you had seen. For example, if I'm having a plain text hello, one second, hello world, whatever it is, hello, how are you, followed by one more hello. What happens is, this is just a vague example I'm giving. If the characters, or you can say if the pairs in the plain text start repeating, and if they are part of some different blocks, for example, these are 5 blocks over here. Just imagine that these are 5 plaintext blocks and these are encrypted with the same key. So what happens is you will get the ciphertext as the same characters. For example, I'm writing something over here. Yes or no? Because the key will be same. Yes or no? The keys are going to remain the same. So whatever, if the plaintext is also same and the key is same, so the ciphertext that will be generated will remain the same for each and every repeated blocks. Yes or no? Am I clear? Yes, right? Because we are using the same key and the operation inside each of the blocks or inside each of the algorithms are going to remain the same. So if the characters in the plaintext start repeating and the key is obviously going to remain the same, then they will generate the same ciphertext block in the output also. This is one of the drawbacks, and we are going to obviously see how to resolve these drawbacks in the next modes of operations. Am I clear? Is the first mode of operation clear? Can write for 5 marks. If the question arises, draw the diagram, explain each and every step. Explanation consists of what is the plain text, how many blocks must be there. Just take an example like I have taken over here. Take a plain text of size 640 bits, divided into 10 blocks, and you will get so and so diagram. Am I clear? So this is the very first mode of operation, that is electronic code book. So I guess we can move on to the next mode of operation, that is cipher block chaining mode, CBC mode. Just check this diagram once and try to understand what is happening. Then I will start with this process. Just have a look at this diagram. Yeah, Brijesh. Guys, if you raise your hand, I just um, feel like you're having some queries or issues. So if you're raising your hands, then kindly ask queries. So try to understand the second type, which is this one, cipher cipher block chaining mode, CBC mode. Just understand the diagram first, try to understand it, and then I will start with the explanation. Very simple diagram. It's just, we can say, an upgrade to the previous one. So can any one of you tell me what exactly is happening over here? Block one cipher text will correct. It is basically a chaining operation. As you know, a chain is nothing but you obviously have studied in chemistry, right? Chains, or we can say chain reactions. So the output of the previous step is nothing but the input of the next step, and so on. Yeah, correct. Cipher कोई XOR हो रहा है. Okay, in chain. Correct. Rohan, so the same thing is happening. Basically, what we are doing is first of all, we need to divide the plain text into number of blocks, right? And there is a concept of an initialization vector. What happens is initialization vector is nothing but a random pixel, or we can say a random value, not a pixel. Computer graphics ke terms of we call it a pixel, but seed pixel. In this case, it is not a seed. It is nothing but a initialization vector of random characters, provided it has to be of the same size as the plain text, because we are doing XOR operation over here, right? So we need some sort of a seed, or we need some sort of an initialization vector of the same size, and using that vector we will encrypt, or we can say we will XOR our plain text block P1, right? So once we get that output of that XOR operation, we need to encrypt it with K. Am I clear? And you will get the result for that particular operation as C1. Once you get C1, you will use it as the seed for the next round. Am I clear? Because initialization vector will be used only once. So whatever output or whatever ciphertext you will get in the first step, you have to use it as an input to the next round's XOR operation. Am I clear? Yes or no? I'm getting some answers. Yeah, block 1 CT will be PT for block 2 using previous cipher for encrypt. Yes, that is exactly what we are doing. Fine. So the same process will keep on continuing. And the second block, for the second block, C1 will be the first input for the XOR operation. And once we get the output of the encrypt operation, that will be C2. And obviously, just make sure that the keys are going to remain same. C2 will now be used as the seed for the next round, and so on. Ultimately, over here for the nth round, it will be Cn minus 1. Clear? So this is how we will get the final ciphertext. Now, can any one of you tell me, does this solve the problem or the drawback of the previous mode? Yes or no? And if yes, then how? What was the drawback of the previous mode? That characters in the ciphertext may repeat. Yes, if the plaintext characters are same. So can any one of you tell me, using this method or using this advanced method or using this upgrade, is the problem of repeated characters solved or not? Come on, give me your answers. Yes or no? Come on, quick. Yes, because the input is getting added with previous cipher block. Yes, the answer is yes. Because what happens is, even if the characters are same, even if the plain text is same, we are encrypting that with the cipher text we obtained in the previous round. Encrypting as in XORing. So what happens is, it ultimately depends upon the ciphertext of the previous round. So even if I'm having two hellos in two separate blocks of the plain text, then also the ciphertext that we're going to generate, or the ciphertext that we're going to get, will be completely different. Yes or no? Because obviously we are XORing it with the previous round's ciphertext. So obviously there won't be any effect whether the characters are repeating in the plain text or not. B division, am I clear? A division is giving me answers. Yes, as the encrypted text of each block will be different. Correct. Jimit, adjacent हुआ तो भी same होगा ना? If the characters are even adjacent to each other, then also depending upon the initialization vector, the output of round one will be different, right? Yes or no? You're not straight away sending the plain text. You're XORing it with some value. And once you XOR it with some value, in this case, if it is the initialization vector, obviously the answer is going to change. Even if the key is same, we are pre-processing it by XORing it with the initialization vector, right? So it ultimately depends upon the initialization vector, which is going to be a random value. Am I correct? Yes or no? Fine. Any doubts with this? Can we move ahead to the decryption part? Fine. So just have a look at this. This is the decryption part. Again, it's very simple. What happens in the decryption is the first input will be the ciphertext C1. We will decrypt it using the key. If you compare it with the previous case, it's exactly similar but in the reverse order. In this case, it was done like this. In this case, it will be done like this. मतलब वही same चीज in the reverse order. So the ciphertext one will be the input. It will be first of all decrypted using K, and whatever result we will get, we have to XOR it with IV. Obviously, the question will arise that how the receiver will know about the IV. It's again based on the same principles that both the senders need to share their keys before the operation begins. So in this case, they have to share their initialization vector with each other before the operation begins. Am I clear? So the same thing happens over here. The ciphertext C1 will be decrypted using the same key K, and whatever result is taken from that particular round, it will be XORed with IV, and you will get back the same plain text P1. Am I clear? Yes or no? Kindly let me know. Fine. Yes, simple enough. Now just have a look carefully what exactly is the input to the next XOR. In the previous case, as we know that the XOR, that is in the case of encryption also, the XOR's input was the ciphertext of the previous round. So that is going to remain the same. As you can see, the XOR's input is nothing but the ciphertext of the previous round. Don't make a mistake. Don't send the plain text over here. Am I clear? Because we want to calculate the plain text only. So we can't send the plain text as an input to XOR. Am I clear? So it will be basically C2 decrypt with K2, and whatever is the result, that will be that will be XORed with the ciphertext of the previous round only. That is going to remain same. Am I clear this time? Yes or no? There are few minor things that you need to focus upon. Otherwise, you might end up doing mistakes. Shall I repeat it once again? Just have a look. During encryption, we saw that whatever was the result of encrypt, that same result was sent as the XOR operation. So over here, what we are doing is, in fact, that was the ciphertext only. So same thing over here, the ciphertext only will be sent as a input, which will be encrypted with the result of this particular operation. And whatever we get, that is your plain text. Am I clear? Yes or no? Same thing only, don't get confused. Fine. Kindly give me your answers. Clear? Fine. The same thing will go on until we receive the last plain text bit. Exactly everything else will remain same. So the highlights of this cipher is each block of plain text is XORed with the previous block of ciphertext, and we make use of random initialization vectors. I will share the notes. Don't worry, no need to take screenshots. I will share it in a PDF format. Each block of plain text is XORed with the previous block of ciphertext. We use a random initialization vector, and even if the plaintext block repeats in the input, the output of the cipher block chaining mode yields totally different ciphertext blocks. I guess, Jimit, your doubt is solved, right? So this is how this particular cipher is improved as compared to the previous one. This is not a cipher actually. This is the principle for principle or mode of operation used by many ciphers. Fine. So these are just the basics, the modes of operations that we are understanding. Based on these 5 modes of operations, ciphers are designed. Fine. So if this is clear, let me move on with the third type. Third one is what we call as cipher feedback mode. This is what we can say a more advanced or a much better cipher as compared to the previous ones. 1 second. It hasn't loaded properly. Just give me a second. Because of network issues, like I said, it's not loaded properly. Yeah, now I have presented in both the tabs. Just wait for a few seconds. It will be shared. Yeah, fine. So just have a look. Yeah, now it's fine. So this is what we call as a third type, which is cipher feedback mode. Is it? It is clear right now. Okay. I guess it is visible. Yeah, fine. So let's move on. This is the third type, which we call as cipher feedback mode. Now, why is this name cipher feedback mode? What exactly we are doing is we are sending the cipher of the previous block to the next block. It is again similar to the previous example, but with very minor but very crucial changes. Just have a look what we are doing. Again, we are making use of an initialization vector over here. That initialization vector is nothing but it is stored inside a 64 bits shift register. I will go step by step. I will go slowly if you want. There is an initialization vector which is stored inside 64 bits shift register. Now the shift register is nothing but a simple register only. We are calling it by the name shift register because we are going to do some shifting later on. Fine. So it is nothing but a 64-bit register inside which we are storing the initialization vector of the same size, that is 64 bits. It is nothing but 1001 binary values only. So combination of zeros and ones. Fine. So what we are doing is we are encrypting that 64-bit shift register with a key of equal size. Fine. There could be any operation happening inside it. So whatever is the operation based on that, we are encrypting the 64-bit shift register itself. Fine. Now what we are doing is we are selecting S bits. Now generally this S is nothing but 8 bits. What we are doing is, let me show you. We are selecting the first S bits, or they can be any S bits randomly. We can select any 8 bits out of that 64-bit shift register. Generally what we do is we generally take the first 8 bits from the left hand side. So we can say that the LSB bits or the MSB bits are selected, the first 8 MSB bits. So in general, we can say that we select only S bits from the encrypted shift register. Am I clear? Yes or no? In general, you can say you can select any any S bits. In general, S could be 8 or any value. Am I clear? Generally, what we do is we keep it of multiple of 8 or a factor of 8 so that multiplications or calculations become easy. So that's why I have taken S is equal to 8. Am I clear? What we do is I will again show you or repeat the process once again quickly. We consider an initialization vector. We store it inside a 64-bit shift register. We encrypt it using a key of the same size. Whatever is the result of the encryption, we select 8 bits out of it. We call those 8 bits as S. Am I clear? Yes or no? Kindly let me know. Yes or no? Yes, fine. Any random 8 bits. Generally, they have to be any random 8 bits, but for simplicity, I'm just saying that you can select any bits. It could be MSB bits or LSB bits, any S bits. But it depends upon the algorithm. Who has designed the algorithm, they will specify which 8 bits to be selected. Otherwise, the receiver will not be able to decrypt the message properly. Okay, so in to keep it simple, I can say that you can select the first 8 MSB bits just for simplicity. Fine. Okay, so once we select those 8 bits, we have to encrypt that, or in short, we have to XOR that with the first 8 bits of the plain text. Am I clear? So what we are doing is we are dividing the plain text into blocks of 8 bits. Yes or no? Irrespective of the size of the plain text, it could be 100 bits in size, it could be 1000 bits in size. What we are doing is we are dividing the plain text into blocks or sub blocks of 8 bits each. Am I clear? Yes or no? Yes, come on, give me your feedback. So yeah, fine. So if the plain text block is assumed to be of 64 bits, we are considering only 8 bits of the plain text at a time. So what we can say that this particular operation or the cipher feedback uses block ciphers as stream ciphers. Yes or no? What we are doing is we are dividing those 64 bits of the plain text also into 8 blocks of 8 bits each. Yes or no? So we are basically treating the block cipher as a stream cipher of smaller size. Correct? Stream cipher में भी वही होता है. We consider each unit as 1 bit. Over here, each unit will be of 8 bits. So the entire block cipher is getting divided into 8 sub block ciphers. Yes? Am I clear? Any doubts with this? Kindly let me know. If not, then I can move ahead. Kindly give me your acknowledgement. This is slightly tricky to understand. Yeah. Okay, Harsh, I'm repeating. That's why I asked, because if you are getting an understanding of this, then it's fine. Otherwise, I can repeat. So what happens is, I will repeat the process quickly. We have to consider an initialization vector of 64 bits. That is basically what we call as a shift register, and encrypt that shift register with a key again of size 64 bits only. Whatever we get as a result, we consider s bits out of it, where s could be any random value. I am considering s to be as 8. Depending upon this value, you have to consider the plaintext bits also. So I am considering 8 bits over here. So I will divide my plain text, which is of size 64-bit block. I will convert that into 8 separate sub blocks of size 8 bits each. Otherwise, how will you perform XOR? Yes or no? It's simple understanding. If you have selected S bits from this step, you must select 8 bits only. Yes or no? If your S is 8, then you must have 8 bits only from the plain text. Otherwise, how will you be in a position to XOR them? Yes or no? So that is the reason we are saying that this block cipher is treated as a stream cipher. Yes, that is the reason. Because stream ciphers are nothing but smaller. We can say that stream ciphers are subsets of block ciphers. Yes or no? Block cipher is the larger set, and stream ciphers are the subsets of them. Fine. So that is what is happening over here. Once you XOR the first 8 bits of that plain text with the 8 bits of the encrypted uh, shift register, you will get the first 8 bits of your ciphertext. Yes or no? The next process I will tell you, but just imagine that you have to do this process 8 times for generating the ciphertext for the first 64 bits. Yes or no? Because after each cycle, you're getting 8 bits ciphertext. So this will continue till 8 times more, and then you will get the ciphertext for one block of plain text of 64 bits. Yes or no? Just let me know. Got it? Fine. Yes, B division. Okay, fine. Fine, Rishikesh. So let's move ahead. Now, why is this called feedback? Just have a look. Whatever answer you got over here, the ciphertext, that will be sent as an input. Basically, that is stored as the shift register. So whatever ciphertext you got over here, ciphertext में क्या मिलेगा? You will get 8 bits, right? So what we are doing is, just have a look. There you can see on top, there's a concept called as S bit shifting. What is it exactly? What is it exactly? Because now you can see that our ciphertext is only of 8 bits. So how are we going to store it or replace the existing 64 bits? Is there any process? Yes, that process is basically what we call as S-bit shifting. What we do is, whatever 64-bit shift register we were having earlier, we have to shift that to the left by 8 bits. So for example, if there are some values over here, we are shifting those values to the 8 bits to the left by 8 bits. All those remaining 8 bits at the fag end will be empty. So what we are doing is, we are copying the ciphertext that we got over here, this 8 bits, into this blank space that is created. Am I able to clear it? Am I able to explain it properly? Yes or no? Kindly let me know. 1, 2, 3, 4, 5, 6, 7, 8. Kindly let me know. I will once again repeat quickly. What I'm saying is, whatever answer you got in the previous step, those 8 bits are copied into the shift register. But how will you do so? 8 bits into 64 bits. For that, what you need to do is, you need to shift the existing shift register of 64 bits by 8 positions to the left, and whatever void is created at the fag end on the right hand side, you have to copy the ciphertext generated in the previous step over there. Is it clear now? Kindly let me know. Fine. Simple enough. So now you will get a complete 64-bit 64-bit shift register for the next round, and this entire process will go on. It will keep on continuing. So now you will get a clear understanding that we had started off with an initialization vector, but as we keep on moving ahead in the cipher, we see that the original initialization vector will be completely replaced by the ciphertext. Yes or no? Because after each step, 8 bits of the original ciphers are going to be replaced by the new ciphertext generated. Yes or no? So even if you have same characters repeating in the plain text block, it will not yield the same character in the ciphertext again and again. This is what we call as the process of confusion and diffusion. You're going to learn it later on, but I'm just giving a brief introduction of that. Fine. So this is the quick recap of the cipher. Just have a look and let me know if you got the understanding of this. Just read it once. The CFB cipher block cipher feedback uses block ciphers as stream ciphers. 64 bits IV is used, which is stored in a 64-bit shift register. Just let me uh, check this out. Do we have to take the same position of S bits? Yes, whichever you settle upon, whatever you agree upon that these are the S bits that I have to select, the same bits you have to keep on continuing for the entire algorithm. You can't change it in between, right? Fine. So the 64-bit shift registers are shifted left by S bits, and and the C1, that is the ciphertext one, is placed in the rightmost S bits of the shift register. So this is just an introduction of the modes of operation. Obviously, researchers are free to change it whichever way they wish. If you wish, you can use the leftmost bits instead of the rightmost bits. It entirely is your call, but the basic fundamental process remains the same. Am I clear? So this is how the cipher feedback chaining works. This is the encryption diagram. Let me show you the decryption one. Again, decryption is exactly the reverse of it. Whatever IV you are having, you will decrypt that IV with K. Okay, I'm going in the exact reverse step. Whatever IV you are having, you will decrypt that IV with the K, that is the key. Now see over here, this is the trickiest part in this algorithm. You have to select those S bits again. This could be 8, and discard the B minus S bits. That is 64 minus 8 bits. You have to discard those 56 bits because those are not required anymore. Yes or no? We simply need those 8 bits. Yes or no? Am I clear? Kindly let me know your answers. We are only interested with the 8 bits that we had got while encryption. So we will just consider those S bits only, and we will discard all the remaining bits. So once we get those 8 bits, that is S bits, we will XOR that with C1, because while decryption we will have access to C1, right? So using that C1, we will XOR that, and whatever result we get, that will be P1. Am I clear? Yes or no? Jimit, just have a look. Over here, if you compare this with this particular thing over here, 64-bit shift register, what we had done is we had only used the ciphertext C1 in the shift register, rightmost 8 bits. So ultimate operation to वो 8 bits के ऊपर ही होने वाला है. Yes or no? So that is what we are doing is we have taken the 64 bits as input, but we are only concerned with the S bits because all the encryption is being done on that 8 bits only, right? So we have to select only those S bits. That is whatever order you select, either leftmost 8 bits or rightmost 8 bits, or every fourth or every eighth bit, whatever option you select, you have to select those 8 bits only, S bits only. And depending upon those S bits, discard the rest of them because we don't need that. Yes or no? Because ultimately we have to XOR with C1, right? Is it clear now? Ultimately those 8 bits are of importance. Rest other bits की मुझे जरूरत ही नहीं है. Am I clear? So this is what happens. Those 8 bits are selected, and those 8 bits will be those 8 bits will be XORed with the input we are having. While decryption, the input will be C1, obviously. So C1 is having those 8 bits. XOR them, and whatever result you get, it will be your plain text P1. If you compare this with the encryption, it is exactly the same, but in the reverse order. In the case of encryption, we XOR the plain text with the encrypted value to get the ciphertext. Over here, what we are doing, we are XORing the ciphertext with the decrypted value of the shift register, and we will get back the plain text. Am I clear? So every cipher you are designing has to follow the same principle. That is, if you are going in one way, there should be a reverse way available for that cipher. Otherwise, whoever is the actual receiver that person also won't be able to decrypt the message. Am I clear? We don't want that. The intended receiver should be able to decrypt it. Fine. So the same thing over here. Now again, left shift it, shift the register b minus s bits. So if b is nothing but block size. So if the block size is 64, it will be shifted by 8 bits. So it will be basically now shifted 8 bits to the left, and whatever s value we got, we have to put it in the remaining 8 bits, rightmost 8 bits, and the entire process will repeat. Am I clear? At the end, we will get a huge stream of uh, ciphertext that is basically 64 bits or a multiple of it. Am I clear? I hope I was able to make you understand these three modes of operation in this lecture. Remaining two modes are left. We'll be completing that in the next lecture. Am I clear? Kindly let me know so that I can stop this lecture over here. Any doubts you're having, you can ask me. Fine. So with that, I can end this lecture over here. Thank you. Thanks a lot. I will just leave in the attendance link. Fine. I will upload the lectures in Classroom after this lecture is over. Fine. Thank you.